Okay, so I think I've dealt with most of the warm-up questions in one form or another, but this is the one I haven't dealt with. So this is comparing the gravitational pull you feel if you were, excuse me, whoa, a little Diet Coke in the morning will give you the burpees. So this is comparing the gravitational pull you'll feel if you were standing on the surface of the Earth at the North Pole at sea level, say, versus if you're standing on the top of Mount Kilimanjaro at the equator. So there are a few factors at work here. First of all, the Earth bulges a bit. It's slightly oblate, so it's got a slightly different radius at the equator than it does at the pole. It's a little wider than it is tall. It's the Earth is, getting to middle age, putting on the pounds, you know how it is, bulging out the middle. Kilimanjaro then rises almost 6 kilometers above sea level. That's what HKJ is here. And so let me be clear that REQ is the equatorial radius. That's why it's EQ. RP is the polar radius of the Earth. And these are slightly different. The Earth also rotates every 24 hours. And that's going to affect someone standing at Mount Kilimanjaro more than someone standing on the pole. In fact, well, a lot more. And here's G. I've taken it to one more significant digit because I want to see how close I can get. One of my students said that if you use slightly more precise numbers, you can get much closer to accepted values of G. So I'm going to just go for like probably 4 sig figs and everything and see how that works. Okay, so let's calculate. First, let's calculate very basically what the acceleration of gravity is for someone standing on the pole, on the North Pole. So AGP is what I'm going to call that. Actually, what am I just going to call it? We're going to assume all the accelerations here from gravity, so I'm just going to call it AP. No, actually, I'm sorry. Acceleration of gravity at the pole. Okay. And so say you've got a mass m. There's you with your mass m. So there's m AGP pole, and you jump in the air or whatever. And so let's see. That's going to be the magnitude of that is going to be just big G times, and this is your mass. So this is actually the force on you. This is the force at the pole. Gravitational force at the pole is going to be G, your mass, Earth's mass, which I'm saying is capital M sub E, over the distance from the center of the Earth to you, which I'm going to say is polar radius of the Earth squared. And that is going to be, so let's just go ahead and plug this in. Let's see. I'm going to define G here. 6.674 E minus 11. And I'm going to say RP is 6,356.8 kilometers, but that is in kilometers. We want to get it in meters, so there it is in meters. Okay, so I'm going to define FP. Okay. Well, and actually, we can cancel. What we really want to find is AP, right? So your acceleration of the pole. So we can cancel these m's here, and then just do G times mass of the Earth. Okay. So mass of the Earth, ME. I'm sorry, I've got a cat on my lap. That's why I'm fumbling a little. I've got to stretch everything else out. And people ask me, why don't I just make the cat move? Because I'm a wuss, basically, is why. Okay. So there is mass of the Earth. Okay, so now we want to find acceleration, AGP, I'm going to call it, at the pole, which is going to be capital G times ME divided by RP squared. Okay, and AGP is then going to be 9.866 meters per second squared. Seems a little high, but okay. So 9, and let's just get the black here. Okay, 9.866 meters per second squared is G at the pole, or acceleration due to gravity at the pole. Okay, force at the equator is going to be mass times acceleration due to gravity at the equator, which is going to equal G, your mass, Earth's mass, over REQ. And actually what I want to do here, Q plus height of Kilimanjaro squared. So actually what I want to do here is do your force on Kilimanjaro and acceleration of gravity on the top of Kilimanjaro. So I'm going to turn those into kJs. I know they're ugly now, but trust me on that. So let's see. So let's cancel that. And I put equal signs up here to imply this is equal to the force. It's not. So let me just scratch that out. And now that I've done that, let me scratch that out. So this is really just literally what you see here equals this, not something else. Okay, so let's do it at the top of Mount Kilimanjaro. Blah, 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 blah. So I'm going to define okay, REQ is just like RP. We're going to take 6378.1 times 1,000. This is going to be REQ. And then I'm going to say R at the top of Kilimanjaro is equal to REQ plus 5,895 meters. So now RKJ is that many meters. Okay, so great. Let's do that. Let's do the same equation as before. Where did I get it? There we go. Except let's do AKJ is G times ME times RKJ squared. And AKJ is 9.78. Okay, 9.782. 9.782 meters per second squared. So you can see what happens is that, you know, as the Earth gets fatter at the poles, or sorry, fatter at the equator, the further you move from the poles to the equator, the lower gravity is because you're further from the center of the Earth. However, there's another factor at play here. Let's say you're standing on top of Mount Kilimanjaro. So I am going to draw Mount Kilimanjaro here, and there's you. And say you are, you know, in the air. You jumped in the air. You're going, whoopee, I'm at the top of Mount Kilimanjaro. And you're accelerating downwards at, you know, A, which is this A here, okay? This is your acceleration due to gravity. However, the surface below you is not actually standing still, right? The Earth is spinning, which means I'm going to draw Kilimanjaro in black. As I drew in black there. So there is black with, you know, lush green stuff on the side. So, and I'll tell the end to the extra question about the 80s band at the end of this. Or I'll tell the answer to that at the end of this video. Sorry. So, as the Earth is rotating, what's happening is the surface of Mount Kilimanjaro is actually accelerating towards the center of the Earth, right? Because if you imagine some rocks up here, you know, this little surface here is circling the Earth. It's moving a circle around the Earth, which means it must be accelerating towards the center. It's going at a constant speed. So, you're accelerating downwards due to gravity, but this is also going through some centripetal acceleration. And so, the apparent gravity you see, which is what we're going to call G, is going to be, it's how fast it looks to you like you're accelerating downwards, given that gravity is pulling you downwards, but also the ground is going away underwards. So G is actually going to equal the acceleration from gravity minus the centripetal acceleration of Kilimanjaro's top underneath you, okay? So what's the centripetal? We've got AG up here, right? So what's the centripetal acceleration for Kilimanjaro? Well, that's going to equal, of course, Kilimanjaro's speed squared divided by its distance from the center of the Earth. Sorry, not kg, kj, which is RKJ, right? However, I'm sorry, what was I saying? Oh, right, we don't know, you know, we don't know this velocity explicitly or the speed explicitly, but we do have a period here, right? So we can do our usual trick where we turn this into 4 pi squared times RKJ over t squared. And this is going to be t, this is going to be the Earth's rotation period, but we convert it into seconds, 4 pi squared, and then RKJ. And this is going to tell us we can find AC here. So let's see what that is going to be. Where's my calculator? There we go. Okay, so AC is 4 times pi squared times RKJ divided by, and then this is going to be the Earth's period, which is 24 hours, times 60 minutes in an hour, times 60 seconds in a minute, and we square all that, and centripetal acceleration there is going to be 0.033 or 337 or 338, let's say 0.0338 meters per second squared. It's not much, but when we subtract it from AKJ, And we could probably do that in our heads, or I could do it in my head, and you guys should be able to do it in your head. AKJ minus AC, you get 9.748. Yeah, 9.748 meters per second squared. So, equals 9.748 meters per second squared. So, this is capital G if you're standing at the top of Mount Kilimanjaro. This is, and so to be clear here, why don't we have to worry about this at the pole? Well, you're standing at the North Pole. Here you are at the North Pole. How is the Earth spinning? It's not spinning, you know, the stuff under you isn't really moving. What's happening with the Earth spinning is it's spinning around you like that because you're at the pole. But the only effect the Earth's rotation has is that if you stand there on the pole, you will turn around in a circle once every 24 hours. But nothing there, you know, if anything, the ground you're standing on is accelerating towards the very pole. So if your foot is like, you know, 10 centimeters away from the pole, then that's going to be accelerating horizontally towards the pole, you know, like if you're standing on a spinning disc or something. But that doesn't matter. That doesn't affect gravity. So this basically at the pole, this is, you know, the G you experience. And this is the G experience on top of Kilimanjaro. So what we're comparing is this gravity you feel at the North Pole or at either pole versus this gravity you feel on top of Mount Kilimanjaro. And if you want to look at those, so we can just say let's see, AP minus AKJ divided by AP. Why did I get that wrong? Oh, probably because I didn't calculate AP. So let's see. Blah, 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 blah. Let's see. Oh, AGP, that's it. Well, whatever. Okay. Actually, it's this. Oh, now it's just getting bad. Anyway, answer was we didn't actually give a variable for the whole thing. So just trust me, this is it. And you multiply that by 100, you'll get a percentage. So this is the percentage difference between the gravity at Kilimanjaro versus the gravity at the North Pole. About 1.2% difference. So probably not enough that you notice. Anybody who's been to both, if any of you have been to both the North Pole and Mount Kilimanjaro, or the South Pole and Mount Kilimanjaro, feel free to comment, you know, whether you felt lighter or what. But that's about what the difference is going to be, 1.2%. Not noticeable to a person probably, but it could be noticeable if you're doing, you know, some moderately precise experiment. So the answer to the question is, or the answer to the question about the 80s band, the line, and if you aren't interested in this, feel free to end the video now. Of course, you're always free to end the video, aren't you? But the line was, it rises like Olympus above the Serengeti, or, yeah, the line I used was, it rises like Olympus above the Serengeti. And I was referring to Mount Kilimanjaro. Above the Serengeti. I won't write it all in. So the song goes, Kilimanjaro rises like Olympus above the Serengeti. Bum, bum, ba-dum, bum, bum. And then the actual title of the song is called Rains in Africa. That's the song. It was from the early 80s, and it was sung by the band Toto. Toto was a one-hit wonder in the 80s. That was their only song that, you know, was at all popular. They were very cheesy, even by 80s standards. But that's the answer, Toto. I had one student out of 100 get it right. So clearly, Toto's legacy does not live on, and the world is obviously way poorer for it. So anyway, there's your whole Kilimanjaro equator question in much more detail than you probably ever wanted.